Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So have this Lambertian model, actually, this leads to the concept of photometric stereo. And this basically is built on this Lambertian model equation. And as you can see that, so this here, this is a matrix of D by 3, and this is 3 by 1. So these images of an object generated by different illuminations can be shown that spanned by a subspace of dimension 3, which is very common result. But in this photometric stereo, basically they study these object-specific samples, which means that you need, since this is a subspace of dimension 3, so you need some basis, subspace basis, which means you need at least 3 images for that object. Okay. But in our case, especially in face recognition, sometimes you just maybe only store 1 image for one object. So you don't have this luxury of storing 3 images for one object. So this leads us to study this generalized photometric stereo. So we want to basically study all appearance of all objects in a class under all illumination conditions. While here, there's just appearance of one object under all illumination conditions. Okay. So this is the generalization we made. And in order to do this, we need to be able to handle class-specific samples, which I'll explain later on. Okay. So here's a key assumption of this generalized photometric stereo. So as I said, we are dealing with a class of object. So what's meaning of saying a class of object? So here's the assumption which actually try to capture this concept. So we assume that this T matrix basically encodes the shape information of that object, and we assume this matrix can be spanned by some basis. So which means that within this class there's some similarities among all these T matrices. So assume that this is a linear combination of these basis matrices. Remember, T is a matrix. So we have some basis matrices, and we can pull out all these T matrices, and what's remaining is this tensor product. Okay. So here this W matrix now actually encodes all the shape information for all these basis objects. So this matrix are common for all human faces. So by the way, if I have questions, just interrupt me and ask me questions. Okay. So here's some derivations based on my assumption. Okay. So we know that image H can be represented as T times F, and we can plug in this linear assumption here, and we can pull out this common T matrices. And what's remaining is a tensor product between F and S. S here is the illumination, and F is this blending coefficient. Okay. So again, as I said, this W matrix is shape information for all human faces, and which means that even I change different H, this is keep fixed. What's changing is if F and S. Okay. So the nice property about this kind of derivation is now the F is illumination-invariant, which means if you change this S, which means that since this illumination is taken into account by this S vector, so the F for the same object, the F is same. So which provides a good candidate for recognition, because we can remove the illumination fact out. And another property of this derivation is this is bilinear in F and S. This is obvious because if we fix S, then this is linear in F, and if we fix F, it is linear in S. Okay. This is similar to this Freeman and Kernel analysis, bilinear analysis. So the main question is basically how can we get this W matrix? Okay. We want to learn this W matrix based on a training set.
How good is the assumption that matrix T can be a linear combination of your bases?
This is quite good assumption. This is actually verified by the experiment I'm going to present. You will see, first off, I show the recognition result. So if if this is not a good assumption, then this F is not a good candidate for illumination-invariant analysis, right? But anyway, I can show by that part. Another part is that actually I can show the W matrix. You can see how good that is. Do you have
How do you determine the dimensionality of T?
T,
Yeah.
the number of bases. T itself, the dimension is fixed. It's D by 3. D is the number of pixels in one image.
Okay.
And the dimension of M,
Yeah.
M is a trick question. Actually, as I did some experiment, and you will see the choice of M actually affects the recognition result. But it turns out a moderate big M, like 100, will be enough. Okay, I can show the recognition results. You will see that. Okay. So now, as I said, I'm going to train this W matrix based on some training set. Okay. So this is the part which is different from this regular bilinear analysis. So we are going to use a very generic training set. So this training set have, say, n training objects, n training images. Okay. And each image is a different person under different illumination. So this is the most generic scenario you can have. Okay. So then if we have this, as I said, each edge can be represented as a W times the inner product between F and S. So we can pull out this common W matrix, and what's remaining is a K matrix. So this basically tells you that there's a factorization between W. There's a factorization for this H matrix. And if you do some rank analysis, then we know that this H matrix is of rank 3m, because usually the number of pixels is much higher than the number of objects using in the training set. And this is bigger than 3m. Okay. So obviously, there are two special cases of this analysis. The first of all, as I said, this can reduce photometric stereo. So basically, we want to study just one object, which means that m is equal to 1. So now this factorization is of rank 3. Okay. And another thing is you can fix the light source direction, which means you reduce the rank for the illumination from 3 to 1. So then this factorization is of rank n. So this is reduced to eigen type of, this is basically reduced to eigenanalysis. Okay. So as I said, we now have this basic equations, H equal to W times K. So this is all we have right now. And we are going to infer this W matrix, right? And in fact, we are going to do more than that. We also don't know all these F and S vectors. So all these things are unknown things. So we are going to, based on this one basic equations, we are going to infer all these knowledges, which is obvious is a very aggressive task. So that's why we need some further knowledges to constrain the solution space. So luckily, we have this type of knowledge we can explore. Okay. So let me explain what are these knowledge. First of all, as I said, this is a rank 3 factorization. So suppose by some means we got some initial conditions of W hat and K hat, then we know that the true solution differs from these initial solutions by a matrix R. R basically is a 3m by 3m matrix. So this basically tells you that we reduce the dimension from D times 3n to 3n by 3n. Okay. Secondary, we know that this K matrix is of a very special form. So basically, each column of this K matrix is a tensor product between F and S. So this further basically provides a compact encoding of the K matrix. So rather than have the full 3n times n degree of freedom, we have basically here each one is n and 3, n plus 3, and times n. So the degree of freedom further reduced. And about this W matrix, there are some nice properties also. As I said, all these T1 to Tm are the shape matrix for each basis object. Okay? And since we are studying the shape, since we are studying the face shape, we can use some shape properties or surface properties, such as that the surface must be integrable, And we are studying phase that we can enforce that phase is sort of bilateral symmetric. Okay. So let's see more details about these two constraints. So first off, this surface integrable constraints. This basically relates to each t part. Okay. So by saying that surface integral, which means that if you find the depth value at x1, y1, and we can go through this integral equations starting from point x0, y0. Okay, this is some integral equations, and we know that this depth value at x1, y1 will keep fixed no matter which integral path you choose. Okay, so this is basically equal to this equation. This is the equation we commonly know for surface. Suppose we have surface zx and y. We know that their second derivative must be same, no matter you change the order of x and y. Okay. So having this, then this is for each pixel, by the way. And for each pixel, we are associated this t vector, basically the product of albedo and unit surface normal. And we can plug in this into this and go through some mathematics. We got this. R of x, y equal to 0. Okay. Now the phase symmetry constraint. So basically, phase is symmetric about this y-axis, as I said. So suppose this is a T matrix, and these are the equations must be satisfied by all this A, B, and C. Basically, each element of the T vector. And again, we can, this kind of constraint is equivalent to this beta x, y equal to 0.
Can you show the T vector again? Go back to
T. Go back to. Okay, so here basically T is the product of the albedo and the surface normal for each pixel, and so this is a 3×1 vector. So for each element I write A, B, and C. Okay. So in addition to this problem, as I said in the beginning, I said initially I am going to exclude all these shadow pixels. Or basically, all these pixels basically violate Lambertian models, where pixels in shadow or in spectral regions or in other things. Okay. So I'm going to use a very simple strategy to exclude those pixels. So I use an indicate function. Basically, if the pixel violates this Lambertian model, I set this to 0. Otherwise, I set this to 1. I'm going to use that. Okay. So, but the question is, we don't know where are these pixels, right? So we also need to infer such function. So having all these components, we are going to put everything together. Okay. So basically, we formalize an optimization problems. So these are the unknown variables. We have this R matrix, which is 3n by 3n matrix, and we have all these f, s, and this this indicate functions for each image. And this minimization is subject to some constraints, which basically try to remove some trivial solutions. Okay. So here's the cost function we have. We have this epsilon, which consists of 3 terms. Okay. The first term, basically, we try to see how this Lambertian model approximates your observation H. So this is approximating error. And the second term is about this integrability terms. We have this alpha, remember. And the second term, we have the symmetry term, we have these betas. Okay. So we're going to formulate all these things together. We put all these things together. So having this optimization, we develop an iterative algorithm to solve this. Obviously, this is not a complex problem. It's kind of, nonlinear problems. So the first step is we can fix R. Fix R, basically, this is the initial solutions. Then basically, we have this W matrix. And we can solve for F and S, and even for tau. And the second round, we want to fix the other things and solve this R matrix. Okay. So let's see how we do that. Okay, so this is step A. Step A, basically, so one thing I should point out is following. Okay. So step A, we are showing this Fs and the tau. All this Fi, Si, and tau I is only related to the image Hi. This does not relate to other images. So, and in addition, these two terms does not include all these unknown variables. So this is equivalent to this. we have a W which is already fixed, we have an H, and we want to solve its corresponding F and S and the tau. Okay, so this is quite easy because, as I said, we're now in a bilinear setting. So we can first fix this F, S, and the tau. We can solve for S. We can solve for F, which basically is linear equations. And second round, we fix F and the tau. We can solve for S, again linear. And thirdly, with all these two fixed, we solve for tau. This is basically try to use the heuristic that, these pixels which violates the Lambertian model will be excluded, which means that the approximation error should be smaller than a pre-specified threshold. Then we are going to use those pixels. Okay. And the step B, computing this R matrix, is a little bit complicated because we have this integrability constraints, which is rather messy, as you have seen. So, but we are able to show that using a vector representation of R, basically we treat each column of this R matrix as a vector. And we do vector derivatives based on that, and set this equal to 0. And after some mathematics manipulations, we have got this type of linear equations. But the coefficient for all these vectors are again a function of R matrix. But anyway, since we are in an iterative setting, we can fix this R and fix this, and we solve for new R, and this process can go on. Okay, so let's see how this algorithm works actually. So here we study a very simple case to illustrate that algorithm. Suppose we have M is just equal to 2. So basically we have two basis objects, and this is basis object under 8 different illumination conditions, and this is second object under the same 8 different same 8 lighting conditions. And what we did is we simply construct a random linear combination of them. So for each image here, we just get some random number and use the addition and to get this image. So this now consists of a training set H. So basically, each image is corresponding to different objects under different illumination. Okay, and we apply this algorithm I just derived, and we're able to recover this W matrix, as I said. Actually, we're able to also recover all these random linear coefficient as well as there's light source directions. Okay, so this is W matrix, and this is a T1 part, this is T2 part. Remember, we have n equal to 2. So this corresponding to this object, and this corresponding to this object. Okay, great. So let's see now how this analysis can be used for recognition. Okay, for recognition we use this CMU PIE database, and this seems the most complicated database available in the literature so far. And this database has 68 objects and under 12 different illumination conditions. And this shows that this is one object and this 12 illumination conditions, and these are, just example images. Okay, so we formulate this is the recognition setting we are using. And for the gallery set, we use 68 images under one set of illuminations. So basically, we form a gallery set by, treating this row as one gallery set. And for a proper set, we are doing a different row. And we want to determine the identities of the proper set by matching with the gallery set. And for the training set, we use a different source, which is different from the PIE database, which exactly shows how we can handle the generalizations of our assumptions, right? So there are two databases available. This is the Yale database. They have 10 objects and under 9 illumination conditions. Another database is Veta's database, which basically is the 3D model. And I just strip away the 3D model and using the albedo and shape information. And they have 100 objects and under 3 illumination conditions. So the strategy is, okay, we have this training set. We learn this W matrix from the training set. We learn the W matrix from the Yale database or the Veta's database. And then with this W matrix given, we can compute the F and S for each images in the gallery and the probe sets, right? This is again. Oh yeah, last question. Sure.
It looks like your energy is saturated. What does that do?
You excuse me?
It looks like a lot of illumination.
My images, right? Okay.
Is that actually true?
This is not actually true. Actually, you are right. Actually, only if the light comes extreme directions, like 0 degree or around 0 degree or around 108 degrees, then the images are most of the pixels are just kind of black. So otherwise, in the reasonable range, actually you got many pixels. Basically follows the Lambertian model. As I said, I actually infer this using indicate function to infer that this pixel is considered or not. Okay. So we are here, right? So we have this W matrix learned from the training set, and for each images in the probe and gallery set, we can learn this F vector, and actually we should also learn this S vector, and we use this F vector to do recognition, as I said. So this vector is illumination-invariant. And we do recognition based on something very simple matrix, which is nearly correlation coefficient. Okay, so here's the result. So suppose, using this Yale database, and suppose we just blindly train an eigenphase approach, or we blindly use this eigenphase, just throw away the illumination conditions, then this is the result. We got 35% on average. Remember, we construct, recognition setting using different illuminations. So we can combine, exhaust all possible combinations, and we compute the average. So we got this. But by considering this illumination using our analysis, we got 67%, which is quite good. But as she pointed out, this is, m is equal to 10. Okay. So now let's say we use this beta database, m now equal to 100. What's the result is 93%, which is actually is almost, I think this is comparable to any method so far. Yeah, you have a question?
Is there a database publicly released or available?
It's public. You can download.
Okay. This is 3D and 3D mesh?
Yes, 3D mesh plus the texture map. And in our case, I convert this to just convert to albedo and surface normal.
What's the number of keeping people that you tested in your test set? 68?
Yeah, 68. Yeah, 68 subjects involved.
So there's 90-something. If the number of test set is more than n, then it's difficult to do the recognition. But if the test set
smaller than n.
Smaller than n.
Yeah, that's a good point. Yeah, but unfortunately, this is the only thing I have right now, so I can't say more on that. Yeah, I believe it's definitely there's the issue involved in this. Ferret, but the case of ferret, they only have 2 illuminations, I believe. So which is not a good candidate for this type of analysis.
So how important were the constraints that you added, the symmetry and integrability constraints that you added to
these constraints are very important in order to recover the W matrix. But once this W is computed, we can just use that to compute the F and S for arbitrary image. So this is important in the. Or if I don't have those constraints, then, as I said, you're right. Basically, you can't do anything based on using this generic training set. Basically, in my training set, I have different objects and different illuminations. You cannot do anything. Yeah. You're right. Yeah. So you have to incorporate all these constraints in order to get a reasonable solution. Yeah, that's correct. You basically 68 objects under a different illumination, different from the training set, different from the gallery set. A human or okay. I see. I really don't know. I have no idea about this. I guess might be similar on this, maybe even a little bit better, you know. Because, you know, most of the recognition error comes from the extreme light source, as I commented out. You know, if your image, you know, is from, you know, like close to 0 and 100 degrees, you know, most of the pixels are just dark. Yeah, as I said, I tried all different combinations, and this is the average rate. I add them together, and some of them are 100%. This is guaranteed. Some of them are like, you know, 8%. So this is the average number. Correct. Yeah.
All the images that you use are very precisely aligned.
That's correct.
So
These are pre-segmented.
But you're going to talk about tracking later, so I assume that you somehow solve the alignment.
Assuming I can do that, actually, yeah. That's correct. Okay, so far I have talked about recognition and the illumination variations, okay? So now I'm going to extend my work to handle pose as well, okay? And keep on tracking time, okay? So again, this is the database I have right now, okay? So this database shows just one object under these 12 different lights and at 9 poses. As you can see, some of them are kind of dark, you know, and some of them are, you know, usually is good, very good. Okay. So this part is I did basically a very simple trick. I'm going to extend my generalized photometric analysis to handle pose as well. Okay. And you notice that I use this concept so-called light field. I guess Michael has more to say about this. But anyway, okay, in my case, or in this concept, or in this context, I treat light source as, you know, I use a very simple thing. Basically, I treat all these images under the same illumination conditions, but at different poses. I treat them as one long vector, say. Okay. So since these images comes from the same light source or illuminated by the same light source, so I can again apply my generalized photometric stereo analysis on top of that. On top of this, basically I denote by L, this L vector, right? So now I got this type of factorization, which is the same. So this basically takes care of this illumination part. So suppose I'm interested in studying this particular view, say V. So basically I'm do some low sampling. I take out those lows corresponding to this particular view. Okay. So if you do low sampling, then you only affect this matrix W. You will not affect what's the remaining thing. So that I have shown that this F vector is both illumination and pose invariant. Because this illumination is incorporated in this part, and the pose is incorporated in this part. So then I do recognition based on my F again. Okay. Okay.
Do you need to have those labeled during training then?
Oh, during training I need labeling, definitely.
You need the same labeling as the
During training, I can label all these images. Okay, this is a particular view.
It's more than you're assuming alignment, and the pose will be known when you will do the
recognition. When I do recognition, the pose is basically should come from this same set. So as I said, this is kind of simple thing. You know, I only have this database right now. I have 9 poses. And so that, you know, the poses actually comes from, you know, all these same sets. But I believe, you know, if you do light field rendering, you can render new views based on this 9 views, then you are able to handle arbitrary view. But so far, I haven't, you know, implemented that part yet. Okay, you want me to explain once again? Okay. So as I said, okay, I have, you know, 9 poles, right? And these 9 poles are illuminated by the same light source, and I treat them as a whole vector. So this is a vector. They are illuminated by the same light source. So each pixel is illuminated by the same light source, right? So this is the only thing I need. And then I can apply this generalized photometric stereo analysis. We can get this equation. This is same, you know. But except that I have this extended vector.
Instead of
Okay, got that? Great. Okay, then as I said, if I'm interested in a particular view, I can do low sampling. This affects this part, and what's remaining, this F is both illumination and pose invariant. That's all. And then I can use this F for recognition again. Okay, so, but I'm going to skip the result and jump to part 2, since I have. Okay, so part 2 is about tracking and recognition. So this part is based on these 3 publications. Okay, so here, this part basically addresses the following challenges. Okay, so we are considering moving objects captured by moving cameras, or captured by moving platforms. Obviously, there are a lot of pose, scale, illumination variations available, and the chances we have a video sequence. Basically, we have multi-frames, and video sequence sometimes we can use this temporal continuity between successive frames. So for tracking, we propose this online appearance modeling approach. And for this video-based recognition, we propose this simultaneous track and recognition. So let's see how we handle that. Okay. So first, for the tracking. So I treat this visual tracking as a stochastic random process, which models both interframe motion change as well as the appearance change happening in the video. So I use this time series model. Basically, so in this model, there are 2 equations are needed. First is observation equation and this state transition equation. And this observation equation, I assume that what you observed is generated by some appearance model and corrupt by some noise. This basically try to handle this appearance change part. And for this state transition equation, I'm going to use some smoothness inherent in the video sequence. And this is try to model this interframe motion part. And again, I use sequential importance sampling or particle filtering to solve that time series model. Okay. So having said that, we know that reliable tracking requires accurate model choices, which is a crucial part for a reliable tracking. So what we propose, we are going to propose some appearance adaptive models. Basically, we want to adapt all these models to the appearance changing happen in the video sequence to achieve a robust tracking. So let's see how we do that. So for the observation equations, as I said, basically we assume that what you observe. Okay, this is your video frame Y, and we assume that some part of the region comes from the appearance model and add some noise. And the key thing is this appearance model. So let me show you this video. You see that. So this video, I'm changing a tank, basically 2 tanks. Okay. So one tank, you can see the appearance change dramatically over time. So basically, this appearance model itself is changing. So it's a function of time t. So rather than it's a fixed temperate. So if you use a fixed temperate, then you are not able to handle the appearance change happening in the video. So on the other extreme, if you keep update your appearance model, basically suppose you have tracked some region at t-1, then you use the track region and use that as your AT. Then the problem is, this track is very prone to drift away. Basically, once there's some drift, you have no chance to rescue that drift. It keeps accumulating that drift. So finally, this will drift away. So the approach we propose is we want to use some mixed model. So we have, as I said, 2 extremes. One is a fixed temperate. Another one is kind of most recent appearance. So what we propose is we basically follow this work and we propose this mixed component. One is the stable component. Try to summarize all past observations. And this component basically try to keep track of the most recent changes happening. And we use a mixture model. And in addition, we need to update this model. As I said, we need to keep track of the change happening in the video sequence. So we use this EM algorithm to update this. And we update this model exponentially. And update this one component just completely. Okay. So another component is this state equation, as I said. So this equation basically governs the target movement. So typically people is assume, so in order to track, say for example, in this case, the object is moving arbitrarily actually because of the camera movement. So in order to track such arbitrary moving object, so we cannot use a pre-learned model basically. If you use a pre-learned motion model, then you're not able to handle arbitrary movement. So what we propose is we're going to use a Markov model, but we want to add adaptive veracity. We try to suppose you have tracked some region at t-1, and what you want is in for the position at t. So there's some gap between t-1 and t. So what we did is we predict this adaptive veracity between t and t-1. And we add this part together, and then we say that, okay, our target follows that motion model. Okay. So this adaptive veracity is actually, we use some first-order prediction strategy. Basically, it's kind of optical flow type of analysis. We can roughly compute where the target moves. Okay. Actually, in this prediction, we need to compute some derivatives, but this actually can be easily done because we already have particle configuration at t-1. But okay. So in addition, as I said, since we use some prediction scheme, obviously we can have some prediction errors, right? So how the prediction is this prediction good or not? So if it is good, which means okay, we're quite confident about the prediction, which means we don't need many particles, so that we can use a small noise variance. This is the noise variance RT, and correspondingly you can use small number of particles. So which basically gains some computational efficiency. So otherwise, we're not confident about the prediction, then we can use a large value of this noise, this variance measurement, and use a large number of particles. So everything is adaptive now. Okay. So as I said, we use sequential importance sampling to compute this particular distribution. Since, in this case, we are in a nonlinear setting and all these noise variables are non-Gaussian. Okay. So in one sentence, this SIS or particle filter is basically a sample version of common filter. So in common filter, basically we based on this, we do prediction based on your state transition equations. You got this, and then you update by your observation likelihood. You got this. Okay. So in common filter, basically, all these distributions are Gaussian, so we only keep track of their mean and the covariance matrix. But in our case, we just use particle filter. Basically, we just use samples and the weights to represent all these distributions. Okay. So now let's see some results. So we're going to track a vehicle. This vehicle is moving very fast, actually, and it's the scale of that vehicle changes dramatically over time. It changes more than 9 times, actually, in terms of the scale. And these are components, as I said. This is the stable component. This is the winding component of that. Okay. So this compares the tracking error. So if we use the adaptive model, then this is the tracking error involved. If you use this fixed template, then this is the error involved. Yeah, question.
How do you learn the adaptive part of the model versus you separate your template into two parts. One that you update exponentially and another that will completely change. How do you identify those two parts?
Identify those two parts.
How do you define them? How do you?
Okay, initially at time t equal to 1, initially I just set them equal. And, as time runs, then I do this EM algorithm, just, automatic update this component.
So you do by hand, you said that you just select it by hand?
In the beginning, I select this patch by hand. I say, I'm going to track this patch over time.
So it seems like under some circumstances, you're wondering if one could actually cancel out the static.
Cancel out? What do you mean by cancel out?
Suppose that you add dark light, like it was dark.
But the issue is I updated the stable component exponentially, so the effect of that component is not, It accumulates over a long period of time only.
So I guess what I'm saying is, without constraints,
Yeah.
the wandering component could be
Could take over?
take over.
I think this is not the case. Actually, the dominant part is a stable component because,
So you have some parameters that set the point is dominant.
I didn't say that I just update the component automatically. So it turns out, always the stable component, takes over. Except there's some rapid appearance change.
Can you explain why that's the case?
That's the case because, you know that if the appearance changes slowly, then, you know that the likelihood, of the appearance generated by the stable component is much higher than generated by the wandering component, right? Because wandering component itself, there's always some small drift. There's some small perturbation, while stable component is rather stable, right? That's it. Yeah. Okay, question.
So how often do you update these if you plug the EMF?
How often? Every frame. Every frame I update that. How fast do the update? Tracking? Okay, so this is now is not real time. This is the main issue. Okay, so I think this is the main issue for a product thing. Okay, but this is not real time definitely. This is 2 frames 1 second, and I use MATLAB implementation. So we are now working on I'm working with a professor trying to come up with a hardware solution for this.
Have you tried to run the common filter rather than the ambiguities?
Common filter is very easy to drift away. Yeah, it's very easy to drift away, especially in the different cases. I have shown the tank, and the first one is the tank, the IR tank, which is the appearance change.
Because of the appearance model or
Because of the
you can always use the adaptive model for common filter.
Okay, so then the question is, as I said, this type of setting is a nonlinear setting, and I don't assume Gaussian distribution. So common filter, I don't think this is the optimal solution here. Yeah, but I believe I didn't try definitely explicitly try extend the common filter type of thing.
How many particles do you have to use?
Actually, as I said, I use adaptive number of particles, right? So actually, I have shown that usually you save many particles. So usually, by this adaptiveness, I use 30% less than regular particle filtering using basically a fixed number of particles.
How many are those? Like in thousands or
100.
100?
Yeah, I use, so regular tracking, I use 100 particles. And for this, on average, I use 70 particles.
I'm a little confused about what exactly are the representation in both cases. So the appearance is obviously the pixel values themselves, but
Yeah.
the particles are just
Particles is affine parameters of that patch. It's the location, scale, and the shear parameters. So this is 6-degree freedom of parameterization
what of the center of the
of the region. Yeah.
what causes the object to be tracking?
What causes object to lose tracking? That's a good question. Yeah, I think basically one example is you have the in-depth location. This is very difficult for this type of tracking. I didn't show some example, but if you have serious in-depth location, which basically varies your affine parameter assumption, then it fails. But otherwise, I think especially you only have appearance change like this IR video thing. We are able to track quite robustly. For minutes, this actually we can see. For example, this video I can track for a long time. For this type of thing. Okay, this one actually recently we developed a multi-view, appearance model. We're able to track very robustly. Suppose your tank is, turning, right? Yeah. So basically you have multi-view setting, and each view we can roughly fit this affine assumption. Then it should be fine. we basically we use this mixture, multi-view appearance model. We don't switch model, we use mixture model.
You have to train the model.
Yeah, definitely. That is true. Particles. Yeah. So right. The goal is basically try to track the target. We are not very interested in capturing the whole distribution of that. The mode.
One mode or
yeah.
multi-mode?
Mode. I try to capture just one mode. That should be enough.
But if it's on one mode, so
common field is
only one mode, it's Gaussian.
Okay, you can argue that you can use Gaussian to approximate unimodal distribution, but I don't think this is the case here.
Because in the parameter space, let's say you have 6 parameters. So the dimension of the parameter space also space is 6. So it's very difficult to
70 particles.
70 particles to cover that region. So kind of very tight.
You're right. It's very tightly supported. The interest is, as I said, I'm only interested in the target positions. I'm not care about other positions. So that's why I don't want waste particles to explore.
Yeah, so some people they may use the parallel quantum filter, like several.
Yeah. They listen to their work using low backwarized particle filter to do this work. Yeah, but we are not, unfortunately, we are not in that setting. We, as I said, they have this mixture modeling, and we have all this in nonlinear setting. So really not the case here. Okay, great. Okay, so this is, we actually expanded this work to the other tracking. So in this video, I showed that this is a two-view. Suppose we apply two independent tracking on these two views. Then, once the accrual happens, basically this part dominates. So we lost tracking in this accrued view. But we're able to use the two-view geometry to infer, based on this tracking and infer the target position in this view. So this is I'm track a pedestrian. So this is also an expanded work. So here, as you can see, the pedestrian is, just off like 30 to 40 pixels in total. So which basically is not difficult to track. And in addition, this is a low construct video and, the slow scale video, of course. So we're able to track the pedestrian quite robustly, I would say. Okay, next question. Okay, so this one actually, I said this is expanded work. So I do both background and the foreground modeling. So I'm not only using foreground model to track the object. I do simultaneous background and foreground modeling. Okay. I'm not actually for the foreground. I'm not using the appearance clue. I'm using the motion clue of that appearance. Yeah. But, okay. Okay. So now this is a video-based recognition. So here is the setting for this video-based recognition. Okay. So we have a number of I have a Gary set which each image is represent one object. And in addition, we have a prop video, which basically provides a number of frames. And we want to identify the object in the video. And this figure shows the appearance happening in the prop videos. And you can see, there are a lot of appearance changes, between the gallery and the prop videos, right? Okay. So again, I adopt a probabilistic approach. Basically, I want to compute this probabilistic distributions of this identity variable. So n basically now is the number of, basically is a random variable, text variable from 1 to big N. Big N is the number of objects in the gallery. Okay, we want to compute these possibility distributions. And in this setting, we have two problems. We have this recognition problem, but in addition, we also have this tracking problems. So we need to take care of these two problems. So the approach we did, we solve these two tasks simultaneously. So let's see what we did. So this is a comparison between typically people will do this tracking then recognition. So they first to track the object, and based on the tracked results, the face image is big enough, okay, maybe we are going to use that. Okay, this essentially is a still image-based recognition, right? Because you just crop up some regions from some frames and do recognition based on that. Okay. What we did is a simultaneous tracking and recognition. We do joint, and the temporal information is used for tracking only. So, but we use this for for both tracking and recognition. This I will show the details. You will see that. And as I said, the recognition performance basically lies on the tracking accuracy. So there's no way that there's no way to study what's the interaction between tracking and recognition, right? But in fact, in this type of setting, these two tasks are related. So we showed that we are able to improve both tracking accuracy and the recognition performance. And we derive a probabilistic approach, so it's rather interpretable. So this is the intuition what we are doing. Okay. So suppose this is the video frame YT, and based on the tracking parameter T, you get out some region from the video frames, and you compare some template in the gallery, indexed by n, and you get some score. And this process just goes on. So mathematically, we have this. Again, we have a time series space model. So the motion equations basically try to use the smoothness between successive frames. And we have this identity equation, which is different from regular approach. So we know that we are observing the same object. So this keeps fixed. So we need these observation equations to establish a link between all these random variables, y, theta, and n. So we assume that what you observe, some part of the video is coming from some template in the gallery. Okay, this is completely specified by likelihood measurement. So as I said, we have two random variables, n and theta, and we observe this y. These are video frames, so we can compute these posterior distributions. So this distribution basically provides a complete statistical description of the product. So suppose you want to find the tracking parameter, then you normalize over this. You got this posterior tracking density. If you are interested in recognition, then you marginalize over theta. You got this posterior recognition densities. Okay. But in order to compute this, if analytically this is very difficult, you have this all integral, all these things, crazy things. Again, we use particle filters. But in this case, actually, one thing notice is this n basically is a discrete random variable. So its sample space is just from 1 to n. So we can come out some efficient computations. Okay. So here's the result. So this is a tracking result. Using the posterior tracking density, you can put a bounding box on that. And this is the scale estimate based on the posterior tracking density. And this is the posterior recognition densities. As you can see, I don't know if you can see or not. Okay. So here, basically, there are big n number of curves. Okay. And as the time goes, the curve corresponding to typically the curve corresponding to the correct identity goes to 1, and all others goes to 0. And initially, we set them all equal probable. So this type of evaluation can be nicely captured by the notion of entropy. Basically, the entropy of this distribution will starting from the maximum value to 0. This is the general case. This is the maximum entropy case. Again, this one? This I use 300 particles. Okay. So what's the question?
So when you start with a random sampling
yeah.
at the beginning, so most of them will diverge and will not converge. So it's not clear why the entropy. So by suggesting that the entropy, you're actually implying that most particles will follow the mode distribution.
Yeah,
it's not clear why this will happen, because many of them on different spaces they will stay.
I know, but that's correct. But these particles will usually have small weight, right? Yeah, right. So this particle has small weight, then I do marginalization, basically you currently capture the mode of your posterior distributions.
And you resample too.
Yeah, of course I do resample. Great. Okay, so let's see how the experiment result works. Okay, so I did the experiment on this NIST database. So this comes from the Human ID project. Okay, so I started 4 cases. Okay, so case 1, basically I just do pure tracking. I throw away the recognition part, and I use a very simple density, Laplacian density, and the tracking is not that accurate. And the case 2, I do both simultaneous tracking and the recognition using this IPS density. Basically, this density is proposed by Mongonda and Pentland, and they show this is rather effective for recognition product. Okay, and by using this, we got this result by like this: 93% tracking accuracy and 83% for the recognition part. And case 3 is kind of interesting. So we just, this is for tracking, and this is for proved effective for recognition. And we just do simple check is using a product of these 2 terms. Hopefully that, we can study the interaction between tracking and the recognitions. Or, hopefully we can use both advantages come from to this different component. And indeed, this is the case. Now the tracking is 100% accurate, and the recognition is improved to 93%. So in this case, I have shown that we are able to improve both tracking accuracy and the recognition performance. Okay. The case 4 is try to simulate this tracking then recognition approach. So basically, this part I just do manual segment all the faces, and then I use this IPS density to do recognition. But unfortunately, this is not that good. Okay, so here comes my summary part. So far I have shown the following. You have this illumination variation and post variations. I'm able to do recognition on top of that. And also I have proposed a generic appearance tracking approach, can track objects like this. And I did this video-based face recognition. Okay. In fact, I have another work is on this kernel learning method. So let me just briefly go over this. So in one sentence, kernel learning basically is try to apply learning algorithms on top of a nonlinear space. So learning algorithms here should depends on dot products. Since this depends on dot products, so this is only characterized second-order statistical information. Okay. So examples about this learning algorithm like SVM, PCA, LDA, and so on. And this nonlinear space is called the reproducing kernel Hilbert space. So this space is induced by this so-called positive definite kernel functions. So the nice property of this function is, this is always constant form that you have a nonlinear mapping phi, and this is the inner product between these 2 things. So once we specify this K function, then we know this inner product we can plug in here. So this basically expands the learning capability of these algorithms. Okay. Since this phi function is nonlinear, so it is able to capture some high-order statistical information. So typical examples of this kernel function are the RBF kernel, polynomial kernel, and so on. So I studied this kernel function basically inspired by this. So actually, we know that different application calls for different data representation. It's not necessarily that the data is in vector form, right? So it comes from different. It can be different examples. As I said, I define an example as a collection of entities with additional structure and attributes. In fact, vector is also obvious is a collection of entities. But there are a lot of other things like, you could have a string graph or, even a statistical manifold, probabilistic distribution matrix, and so on. So if we are able to propose, kernels between these different examples, then we can plug it into the SVM. And we can come out some, classifiers which can classify all these different things. So recently I proposed this trace and the determinant kernels between matrices. Basically, I use a matrix to as my input. I have shown that this trace kernel here, X and Y are 2 matrices. And if you have inner product and you take trace, then this is a kernel function. And if you have Again, if I determinant of this quantity, this is also a kernel function. The nice thing about this thing is you have a matrix here. So we know that usually people will think that a class of matrix is equivalent if they have the same column space matrices. Then you can plug in the column space matrix into this kernel, so you can come up with something which characterizes a class of matrices, right? And also here, since this is inner product between two matrices, we can actually use kernelized matrix. Basically, this matrix kernelize each column. And we can plug in a kernel matrix, a dot product matrix in here. So basically, it's able to characterize some high order statistics about columns of the matrices. Okay. So in addition, we can construct this polynomial kernel for matrices like this, and RDF kernel for matrix like this. Also, you can combine all these things, kernelized matrix, plug in here, and get something. These are also kernel functions. So the nice thing about this construction is the following, actually. So we are able to utilize capture some spatial correlations between different columns. So rather, if you treat matrix, vectorize it, you lose that information. Okay. Another thing actually I did is I proposed this probabilistic distance in RKHS space. So we know that there are a lot of probabilistic distance like Chernow, Bhattacharya, Mahalana disk, KL distance. These are very useful quantities in different principles. But if we assume that your data admits a non-parametric density, then these distributions are very hard to compute in the original data space. Because then this distance involves integrals basically. But if you assume that the data admits a parametric densities, then there are analytic expressions, but these parametric densities are hard to model non-linearities available in the data. So the solution, what I propose is that I'm going to use this Gaussian density in this RKHS space, and basically I'm able to use this analytic expressions, but with some non-linearities characterized, since I'm using this kernel mapping. Okay, I have 1 minute. Okay. So actually, I have some book chapters, but I'm going to skip that. It's not important. Okay. So here's the future work. Okay. So I believe my future is in this communication correlation and the signal processing. And for this communication and collaboration applications, such as distributed meeting, automatic lecture room, all these things, I think these systems is able to expand it by the following bullets, which I can make some contribution, I believe. For example, we usually in this distribution we should track a group of people, and we need to associate different identities using face or even voice clues rather than you pre-register your system. And also we need to monitor different activities happening in this lecture room or meeting room. And detecting events is also important. We need to hopefully this system can act some event. Another thing is missing for this automatic lecture room is we should be able to do some offline lecture editing rather than do online. Because offline basically gives you more room and time to come up with some nice things. Okay. So for statistical media processing, I think I can make some contributions on classification, clustering, and enhancement, as you have seen. So in the long term, I think I share the vision that compute will become a multimedia processing center. So I believe that in order to achieve this goal, a lot, researchers from different disciplines should come together. And I think I'm working on this key component along these lines. I'm working on machine learning and data mining, and as well as optimizations. I'll end my talk with my thanks slide. Thank you so much.
One or two very quick with the tracking and the illumination.
Okay.
You do particle filtering in the discrete space.
In the discrete.
The names of the identities.
As well as the tracking parameter. It's joint distribution.
Because when you do the resampling, would you allow for neighboring identities, or that's not too clear how you do with the resampling? Once you compute the weights of the hypothesis, how would you?
So each joint pair of identity and the tracking parameter has a weight, right? And based on their weight, I can do resampling. Is that correct? Right?
Well, it's clear in a continuous space, but in a
Discrete space, you can still do that. I don't think there's some limitations. You can do that. So basically, this is discrete. You don't have noise for this, identity parameters. You don't add noise. That's all. But still, you can do resampling. Okay, maybe we can talk offline if you want to form more details. Great, thank you.
Why do you bother having samples in that discrete space since you don't have that many dimensions? You don't have that many people.
I don't have that many people.
So you could just have a probability table for the posterior, for the identity, and then sample the conditional location given the identity.
Actually, I think I mentioned I have some efficient computations based on that. This actually try to use that fact. This is discrete and available. I can exhaust the sample space. You're right. You can check the details.
Yeah, you can just exhaustively do that one, and then do the other one, conditional.
That's other one.
Is that what you could do?
This is I did.
Okay.
Thank you. That's a good point.
Good, yeah. Should bring that up.
I mentioned one, I didn't emphasize that,
my reason that I was confused before was that I thought that you were saying you had a template for the constant part plus a varying template that was added together.
This could be combined actually.
But they're not. You don't add them up.
I don't.
You separately. You're tracking both as if they were separate likelihood.
As if, yeah.
You're not saying I'm going to have one template, which is the sum, the linear sum of constant part and time variable.
What did you say?
So what I had understood at first was that you had the template that you were tracking was had a constant part added to a time variant, not a constant part.
The first part, for the tracking part, right?
Yeah.
Actually, you can combine these two things together. As I said,
But in yours, they're not combined.
In the current, implementation, I didn't combine. Okay, I tell you what. Okay, this is what the track and recognition stuff comes before the visual tracking part. Okay, so I didn't combine them together. But later on, actually, I did some combinations. I combined this visual track with my tracking and recognition framework, and get some good results.
So I had really hoped that you were going to talk about, going back to the first thing, I really hoped that you were going to talk about that, number one, as a generative model. And number two, I thought you were going to talk about tracking with rotations and depth, faces with rotations and depth, and lighting changes.
Oh, I didn't.
Not there yet.
See, the thing is, I have different researches.
Yeah.
Okay,
no,
these.
The same thing.
Yeah, right. The part 2 part comes before that.
Exactly like yours. Like here's my audio sound separation. Here's my face tracking stuff. Here's some other face tracking stuff that's completely different.
You're right. I didn't come up complete system. Okay, I can take all this.
No. That's not. I'm not complaining about that. What I'm wondering is, is that something that you want to do? Do you want to take what you've done with the lighting and pose?
I can combine all these things together.
Combine that with tracking.
Yeah.
Because that would